Which masking situation is more difficult? If the signal and masker are in the same location, or if the signal and masker are separated? Perceived separation of sources leads to a spatial release from masking. That means that spatial release from mask. That means that if they separated masker and the signal, you get a better intelligibility. Interval time difference. ITD leads to perceptual separation of target and interferer. Yeah. Larger ITD leads to a larger advantage. Okay. Yes. Okay. ITD and ILD and HRTFs. ITDs and ILDs introduce an advantage. The full head-related transfer function FF leads to an even larger advantage. Okay. So if there's a graph here with the ITDs in milliseconds, with first axis increasing from 0 milliseconds to 0.75 milliseconds. Then the SRT speech reception thresholds in dB are going better. Yeah. Yes, it's in threshold is better. It's easier to catch words. Better listening understanding. Which ear listening is best? Which situation is more difficult? Signal and two maskers together. Signal separate from two maskers, but the two maskers are together, or if you have a signal and masker symmetrical about the masker. Auditorium system can use the ear with a better SNR. Speech intelligibility is reduced when maskers are symmetric. Then it comes to the listener. What are factors about the listener influence the ability to understand speech? It could be hearing loss. For instance, hearing loss in decibels. When you are 20 years, you have almost no hearing loss from 125 hertz to 8 kilohertz. And the hearing loss is increasing when you get 30, 40, 50, 60, and 70 years. It should be in this curves 8 kilohertz hearing loss when you are 70 years old, about 60 decibel. You have auditory spread of masking, auditory filters, upward spread of masking. For low pass noise, there's a normal hearing frequency. Normal hearing frequency is not that big. From impaired listeners, the frequency is bigger. That's what I'm saying here. That is, you have auditory filters for normal ears and impaired ears. The auditory filters for the impaired ears are much more broad than for normal ears. What do we want the listener to do? Why might it affect the results? Now we come to predicting speech intelligibility. We have some methods: articulation index AI, speech intelligibility index SII, speech transmission index STI, and then from DTU speech envelope power spectrum model here from DTU, and there are also others. What is in articulation index? From published in '69. I will do it shortly. We have some n, for instance, n frequency bands, and we assume that contribution from each band is independent. Then we have a internal metric. It ranges from 0 to 1. and then an AI number between 0 and 1, and it must be converted to intelligibility afterwards. It's the same as a sum from ID 1 to n of a product of the importance of frequency band E and the audibility in band E. The audibility is a function of hearing threshold and noise masking. So this sum, yes, and we can say acoustic measurements for each band. Speech level, we have speech level, and a noise level we don't know. Hearing threshold, we calculate the masking noise level. Index I, band E, band I mean, is the speech level minus maximum of threshold and noise. And then we adjust AI to stay between 0 and 30. If the audibility in band I is less than 0, we set it to 0. If it's more than 30, we set it to 30. Okay, we got a number. It's a sum of n contributions. With each frequency band has an importance, a weighting, you can say. So we converted AI to intelligibility. If your sentences are well known, it's easy to capture, then articulation index don't have to be only small to get a high percentage of syllables, words, or sentences understood correctly. Or else, if it's unknown or nonsense words, you need a higher articulation index, you can say. You can also say there's some correction for visual cues. The effective articulation index increases a little bit with visual cues if you can see the person speak. Yeah, yeah. Yes, okay. Mm. Speech intelligibility (SII) is the same concept as before. Three input measures: speech level, noise level, and threshold level. Standard includes data for EI, speech level, and hearing threshold. Only need to measure sound. So it's the same formula, but something about the speech spectrum is increased. Something we also include shouting persons and so on. Yeah. We can't model everything. Scope predictions are correct only on the average, that is, across a group of talkers and a group of listeners of both genders. Predictions are correct only on the average, that is, across a group of talkers and a group of listeners of both genders. Is limited to natural speech, normal hearing, stationary masking noise, so on. Then we have the speech, predicting speech intelligibility using the modulation domain. How can we account for reverberation? SNR, signal noise to ratio, signal to noise ratio based filters do not work. Doesn't account for signal interfering with itself. For instance, a reverberation. We need a new filter metric. We still have this function of inner hair cells transformation from mechanical to interstellar potentials. From low frequencies, we use a fine structure. It will use high frequency. It's in the envelope. Yes. Temporal modulations are the rates of changes in amplitude of the intensity envelope. Okay. Temporal modulations are the rates of changes in the amplitude of the intensity envelope. Simple hair cell model. We have a half wave reflection, you know about this stereocilious bending to the right, it gives. Then the emission, and if to the left, no passing. It's this rectification plus low pass filtering. Yeah. Center frequency about 1 kilohertz. Okay, we have a speaker. We have a transmitted speech signal modulation index m equals 1 from the speaker. Yes, it's a formula included cosinus. Then we know it also from this Planck reserved, and then we have a research speech signal modulation index m less than 1. Okay, this received speeches. M is in the modulation depth. So for the speaker is 1, and for the receivers is less than 1. Then we have some modulation transfer function. And the modulation transfer function is a fraction between the modulation index for the receivers divided by the modulation index for the speaker. And this last one is 1. Modulation frequency. It is decreasing in a way when the modulation frequency is increasing from half to 16 or something. And then we get an STI transmission index. Modulation can be reduced by added noise, reverberation, distortion, for instance peak clipping. Principle: reduced modulations gives reduced intelligibility. Then after there comes some, we have, for instance, 7 octave bands, K index, and we have some modulations, maybe 14 modulation frequencies difference. After measurements of the MTF, the modulation index for each modulation frequency and each audio frequency band is converted to an SNR. We get an SNR with index K and F. It's 10 times log 10 mk. This m modulation divided 1 minus m. This m is a fraction between m2 divided by m1 as before. We have those SNRs are between minus 15 and plus 15. The SNR values are normalized to values between 0 and 1, which are called the transmission index values. We have this SNR, and then in the denominator add 15, and the whole thing is divided by 30. The overall STI value is calculated as an average over all the modulation frequencies and a weight sum of all the frequency bands. We have 14 frequency bands and 7 octave bands. So its STI is a sum of K1 to 7 octave bands of a weight number alpha K times 1 divided by 14 times the sum of all those 14 transmission index values. Then we translate it to intelligibility. Yeah. And then we have also RASTI. It's easy. It's only with 2 octave bands, 500 Hz and 2000 Hz, and a smaller number of modulation frequencies. Yes, STI originally developed for measurements in rooms. And blah blah blah. That's what I get here.